going to be a SOLIDWORKS analysis for airflow over various geometries in an attempt to optimize aerodynamic efficiency. Shell shown is a streamlined configuration, uses an FPV racing drone, and will be the one used in this demonstration on how to create the flow over the shells. We're now going to walk through how to perform the external flow simulation on the shell. First thing you're going to need to do is go to Tools and then Add-ins. Next you're going to click Flow Simulations. From here you're going to want to go to the Flow Simulations tab. From there you go to Wizard. Here's where you're going to set your project name. Going to click Next. Here's where you define your units. We're going to be using SI. We're going to do external flow, so we'll go through there. Here's where we're going to define the working fluid. We're going to click air. We're going to add it to the project fluids and click Next. I'm going to click Next through this. And here's where we'll define the velocity of the air. As you can see, the velocity we want to be traveling is in the Z direction. So we are going to set it to be 26.82 meters per second. That's 60 miles per hour, which is the standard racing drone speed. The next thing with this model created, we're going to want to set some goals. The first thing is to go to insert a global goal. What we're going to be looking for is force, and that's going to be in the Z direction here. Click that and click the goal. The next thing is we're going to want to insert an equation-driven goal. So first we're going to click the global variable we just set, the force. And this equation-driven goal is based off of this equation here. That's the equation for the coefficient of drag. It's based on a few different things. The projected area, which is the area seen on the front of the drone. We've also got the velocity again, and the density. That's at 5,000 feet, which is where this drone is expected to perform. So we got the denominator set up with that value for that equation. We're going to plug it in over here, multiply by 2, and divide by that denominator. And we're going to want to set this to unitless, so we'll do that and hit the green check mark. You can also set what your equation is looking for. We got the coefficient of drag. So what we're going to want to do here is we're going to want to run the study. There's nothing you need to do in this window. You'll just go ahead and click Run. So it'll open up a new window for the flow analysis. What's going on here is it's setting up the mesh, which is basically just looking at various points on the geometry and setting those up. It'll take a few minutes to calculate here, so it'll be a minute. One thing you can do is you can go up to the flag up there, and that'll give you a status of how your calculation's going. We will go ahead and go over to another analysis we performed on just a standard cube to show the differences in the drag force. Here we're going to go ahead and open the same equation goal. This is going to show us the drag force once we load the results here. Going to take a look at that. And here we can see a coefficient of drag. It comes out to be about 1.25 after it's converged. That's editable. Another thing you can do here is you can insert a cut plot. One thing useful to do there, we'll be looking at the front face of the drone there. What we can look for is the velocity in the Z direction. That'll give us kind of a profile. We're going to want to smooth the slider all the way over to the right. That will increase the resolution and hit the check mark. And as you can see now, we have a nice little profile of the velocity along the face and around the sides of this cube shell. Which is pretty useful. So that's basically what you get out of running this analysis. When we performed the same analysis on the regular shell, it's still running, but we got a drag force of 0.52. That is reduced by about 70% from the one we found on this cube, and that's a significant decrease. That's shown that we can definitely optimize the efficiency of the shell, but ultimately it all comes down to your skill as a pilot. And as you see, if you suck as a pilot, you're still gonna have a bad time. Thanks, guys.